Hello everyone, this is Mr. Arias and this is my video on impulse momentum theorem. Now I have to warn you, this is actually a re-recording of the audio because when I was filming this, I already narrated and then I realized later on that my audio was a little bit squeaky for some reason. But here I am trying to record the proper audio now over what I did earlier, so please bear with me. So anyway, impulse and momentum are defined as such. So you have impulse is equal to F delta T and momentum is equal to m delta v. Okay, and basically this all comes from F is equal to ma, which is Newton's second law. Now if we get this, a is equal to basically the change of velocity over the change of time, and therefore all you need to do is rearrange this to get that F delta t is equal to m delta v, and this is the impulse momentum theorem. So let's take a look at what this means for something like this. So the problem goes this way. Okay, the velocity of a pitched baseball has a magnitude of 45.0 meters per second, and the batted ball's velocity is 55 meters per second in the opposite direction. Find the magnitude of the average force applied by the bat on the ball if it remains in contact for 2 milliseconds. The baseball has a mass of 0.145 kilograms. So basically, when we're given a problem like this, let's take a look at what values we're given. So we have 45 meters per second. Okay, that's the velocity of your baseball before, and 55 is the one after. Okay, and opposite direction is also important. The time that we're given is 2 milliseconds, and the mass that we're given is 0.145 kilograms. Okay, so now let's take a look how we're going to solve this. So let's list down what we have. Your VI is simply going to be 45 meters per second. Okay, now one thing that I will do will be I will be setting this in the negative direction because it's coming towards the batter. Okay, it's not flying forward away from the batter, so I'm going to set it to negative. But in theory, you should be able to set it either way. As long as the convention that you use is consistent, you should be fine. Okay, so negative 45 meters per second initial, and final is 55 meters per second. Okay, and you also have to take note that the average force is in contact with the bat for 2 milliseconds. Okay, and the bat has 0.145 kilograms, so the mass is 0.145 kilograms, and okay, the time is equal to 2.00 milliseconds. Okay, however, one thing to take note of would be that it's not an SI unit. You need the SI unit if you want to use things like newtons, because definitely that will have a factor in that kilogram multiplied by meter per second squared is equal to newton. Okay, so if you have milliseconds as your unit of time, you have to convert it into the proper SI unit, which is seconds. Okay, so with that in mind, let's do it. So time is equal to 2.00 milliseconds, and we know that there are 1,000 milliseconds per 1 second. Okay, so let me just write this down. So that's 1,000 milliseconds and 1 second on the top, and basically cancel out, and you're going to be left with, okay, get the calculator. So 2 divided by 1,000 gives me this fraction. However, if I want to make sure that it's a numerical form, I press ST, and that will give me 2 times 10 to the negative 3 seconds. Okay, so there is my unit of time. So time is simply equal to 2 times 10 to the negative 3 seconds. Okay, so now I have all of my given values on one side. Let's do this. Okay, so VI, VF, M, okay, and T, once converted, 2.00 times 10 to the negative 3 seconds. What are we required to solve? We are required to solve for force. Okay, that's given in the problem. Okay, and basically we're just going to use, okay, so that's average force. And to get average force, we will just use the equation that we wrote on the top, which is J is equal to P. However, we have to take note that J is equal to F delta T and P is equal to M delta V. Okay, so now that we have those, we can solve for what we are given in the problem. Okay, so let's take a look. So F delta T is equal to m delta v. Okay, but we could rearrange this to isolate force on one side. So that will become force is equal to, okay, m delta v over delta t. Okay, so that is the equation. And then once we have that, we can just simply plug in the values. Okay, so mass is 0.145 kilograms, right? And now what we want is our change of velocity. We have to note that change of velocity is always final minus initial. So if that is the case, then it's going to be 55 meters per second, okay, minus initial, so that's minus negative 45, which becomes, okay, what's minus negative? That becomes positive 45 plus 45 meters per second. Okay, and that is all over how much time the collision took place. In this case, that's 2 milliseconds, or 2.00 times 10 to the negative 3 seconds. Okay, so it looks pretty daunting and intimidating with all the huge numbers, and I understand the intimidation, but once you have it in this format, all you need to do is plug it into your calculator, and you should be able to understand what you're going to go into. Okay, so let's get our calculator out. Okay, let's try to plug everything in. Okay, so I just have to wait for the person because I'm again narrating over something I did earlier. So anyway, 0.145, okay, times 55 plus 45 all over, okay, 2 times 10 to the negative 3 seconds. Okay, so once all of this is laid out, let's press the equal sign. That becomes 7,250 newtons. Okay, so that is the final answer. Your value is 7,250 newtons. Okay, because you know that kilogram times meter per second squared is newtons. So 7,250 newtons. And it kind of makes sense if you think about it, because it takes a lot of force for something that's moving so fast at you to then go the exact opposite direction at a much faster speed. Okay, so therefore the answer 7,250 newtons. And if we try to account for significant figures, we've used 3 significant figures consistently all throughout, so it should be the same thing, 7,250 newtons, consistent. Okay, so that's the final answer, and I hope that will enlighten you in this kind of problem, impulse momentum. On our next video, we will now tackle collisions. Okay, so take care and bye-bye.